Okay, let's start lecture 6, which is the last lecture of part 1. In the lecture 5, we have learned how to calculate the carrier concentration in the semiconductor. So basically, we have both electrons and then holes in the semiconductor. And so for both electron and holes, and we have two sources for generating movable carriers. So one is the intrinsic mechanism, and the other is extrinsic. So once we know the carrier concentrations, so now we are in the position to talk about electrical conduction in the semiconductor. So this means that when you apply a driving force, so typically is an electromotive force or electric field, and then these carriers will try to drift. And so when they start to drift, and then we'll have the current flowing in the semiconductor. So before we talk about the electrical conduction, we just have a recap of lecture 5 again. So in lecture 5, so basically we said that we have two mechanisms. So one is intrinsic and the other one is extrinsic, which can be used to generate free carriers. So in the intrinsic case, so what we do is that we use a thermal excitation and to excite electrons from a valence band to conduction band. This is always happening at a finite temperature, regardless of the size of the band gap, right? So from a simple statistics, so we can find out the intrinsic carrier concentration, which is given by this equation. So we can see that once the semiconductor is given, and so some of these parameters are basically known, and then so intrinsic carrier concentration is only dependent on temperature and then band gap, right? So so eventually we introduce two very useful parameters. So one called NC, another NV. So NC is the effective density of states of the conduction in the conduction band, and the NV is the effective density of states in the valence band. So both have a unit of concentration, basically the number per unit volume. So that's the reason why the product then take a square root, and this overall will give you a unit of carrier concentration, right? And we also estimate what's the NC at the room temperature. And so at room temperature, so roughly, so this is the value. So this means that this value, of course, is much smaller than that of carriers in a metal, about 100 times smaller. And then, of course, it depends very much on this number. So, and then we can try to use this to reduce this carrier concentration further. So eventually, you can see that the carrier concentration, intrinsic carrier concentration, actually is very low in the semiconductor with a band gap of about one electron volt. Okay, and then since this is not a very effective mechanism to generate free carriers, and then people have found other way to do that. So the most common way to do it is to dope the semiconductors by impurities. So we have two types of impurities. So one is called donor, and the other one is called acceptor. So donor will contribute free electrons, and when they are analyzed, and the acceptor will contribute free holes. So the extrinsic carrier in the intermediate temperature range is given like this. And then this, you can, we already explained this one in lecture 5. So we just look at the two equations again, and they are very much, similar, right? So, so this part is, very similar, and then this part is also very similar, right? The only difference that, so for intrinsic semiconductor, you have band gap here, and then for this extrinsic semiconductor, you have this so-called donor ionization energy here, right? And since this value is much smaller than a band gap, so that's the reason why at the same temperature is much easier to generate the free carriers using extrinsic mechanism compared to this intrinsic mechanism. So the ratio can be as large as this. So for example, so this basically look at this prefactor, and so this one divided by this, and you can see it's very, very small, right? That's because this band gap is much larger than this ionization energy, right? So effectively, so you may, of course, this is not the physical picture. I mean, is effectively some sort of picture for you to understand so what's going on in this extrinsic semiconductor. So this means that this extrinsic semiconductor can be divided into two intrinsic semiconductors. So one, of course, is the host semiconductor with a pretty large band gap. So that's the reason why it's not so effective to generate a free carrier by using this intrinsic semiconductor. And the other one, so basically the dopant itself, can also be considered as some sort of intrinsic semiconductor with a very, very small band gap, right? So, and then the EF will be at the middle between this conduction band edge and then this donor energy level, right? So for intrinsic semiconductor case, so this is EF is in the middle of the band gap, right? It's similar. So, but in this case, it's very easy to excite carrier from this dopant energy level to conduction band because this gap is very, very small, compared to this one, right? So this is one difference. And the other difference is that, so in this case, when you generate free carriers, so you generate both holes and electrons at the same time, simultaneously. So that's the reason why you cannot actually control the conduction type of these intrinsic semiconductors because you have an equal number of holes and then the electrons. Excuse me. However, for extrinsic case, and then if you have a donor dopants, and then you basically produce electrons only. And then if you acceptors, and then you just produce hole only. So this means that in addition to carrier concentration, and then the extrinsic mechanism also allows you to control the type of conduction, which is extremely important. Okay, with this, I will look at electrical conduction in semiconductors. So before that, just look at what's going on in metals first, because in the metal case is very simple. You only have one type of carrier, which is electron, right? So that's why it's good to look at some of the basic concepts in metal first. Okay, as I already explained in this module, and so inside the metal, so what happens is that you have a huge number of electrons per unit volume. So this means that your electron density is very high. And however, since electrons are moving in all different random directions, so that's why if you don't apply any electric field, so this means that the net current inside this material is always zero. This means that's because the electrons are moving in random directions. And however, if you apply electric field in a certain direction across this metal, and of course, then electrons are still moving at a very high speed to all different random directions. But against the field direction, there will be a small drift of these electrons. So this drift basically will give you the electric current. And the simplest way to release the current to the electric potential drop across the two terminal of a conductor is the Ohm's law, right? So this basically is called macroscopic Ohm's law. So in this Ohm's law, you can see that we have three physical quantities. So one is called voltage, and the other one is current, and then the third one is the resistance. So here I have a question for you. Although I believe all of you are familiar with this Ohm's law, right? So and do you have the current first, or do you have voltage first in this case? Okay, so you may think about this. So the question I ask you is, since you have voltage and current in this Ohm's law, right? So the question I ask you is, do you have current first or voltage first? Or in another way, does current come first or voltage comes first? Okay. So most of you, I believe, will see that you apply voltage, all right, and then you measure the current, and so the product in the current resistance basically is equal to the voltage. But this picture actually is not very accurate. So in fact, what happens is that current, so in order for current to flow, and what you need to apply is not voltage, it's the electromotive force, basically the driving force, right? That basically comes from the battery self-damper, okay? So this electromotive force will force the electron to flow through the conductor. So when electron flows through the conductor, so electron will be scattered, right, due to defects, less vibration, and then also other electrons. So eventually, and so electron will feel the resistance. So once you feel the resistance, and then there will be a buildup of electric potential. So this means that the electric potential at these two sides will be different. So the difference between the electric potential at the two terminal, so that basically is the voltage. So this means in that sense, and actually you have current first, and then you have the voltage, right? So that because you have to force current to flow, right? So that should be the right picture. Okay. So now, and also this Ohm's law and it's called macroscopic Ohm's law, and so it's a, I mean, it's a quite a important relation which you can use to describe this current flow in a conductor. And of course, there are many assumptions. So for example, so here, so basically, you don't see, for example, electric field or current density, all of this. So basically put everything together and then take the average. So look at the macroscopic value, right? So, but we want to understand the physics, and then we have to somehow replace this macroscopic physical quantity by some microscopic physical quantities, right? So now we know that this so-called voltage, electric potential difference, right, between the two terminal. So basically you can buy, so if it's a uniform, right? So if the electric field is uniform, and then begin by L cross E, sorry, L multiplied by E, right? So electric field multiplied by the length. Suppose that the E is uniform. Okay? And the I, of course, is given by the current density multiplied by this cross-section area. So again, we assume that this current density is uniform, and then you can do this, right? So R, based on Ohm's law, so it's another Ohm's law. So it's given by resistivity multiplied by the length of this conductor divided by the cross-section area. So of course, again, we assume that the rho is a constant, is uniform, so the material is uniform, and then S is the same across this length, right? So it's all these assumptions, and then now we just substitute so this VIR into this equation, and then you can see that you have this one, right? So eventually, so I can say S cancel out, and this L cancel out. Then you have a current density, which is given by electric field divided by rho as the resistivity, and then 1 over rho is the conductivity. So this is a very important equation. So this means the current density is equal to sigma E. Okay, so this equation is more powerful than this V equals AR. So why this is the case is because that this J and the sigma, J and the U and the sigma can be a local variable. So this means that J is a function of position variable, right? And then E, and of course, is also dependent on the position, right? Sigma is the same. So this means that J and E is also called microscopic, right? So microscopic. So this means that microscopic parameter means that you can define this locally for each point inside the conductor, right? So this means that even this non-uniform, so it doesn't matter, and then you still can use it. And however, so this equation is called macroscopic. This means that you lump up everything together. So if it's not uniform, then you have to do the integration. If it's non-uniform, you have to do the integration, right? So you get to the macroscopic value and then return to each other. So, but the macroscopic equation is much better, right? Because it's really related to the microscopic properties of this conductor. Okay. So now you can see that for the same electric field you applied, and how much current you can get, very much in the conductivity, right? So now we look at the conductivity. So how is the conductivity related to other microscopic properties of the material? So now let's look at the basic electron transport. So suppose you have a vacuum, right? So inside the vacuum, you have a number of electrons. So now if you apply a driving force to this electric field to this, And then of course, electron will start to move. When electron starts to move, if it's a vacuum, and then if there's no scattering between all these electrons themselves, right? And then since the vacuum there's nothing inside, unless you hit the boundary, so otherwise, and the moment of this electron can be described by this Newton's second law, right? So this means that this is the mass, and then this dv is the velocity. So dv dt is acceleration. So this the product of m and then acceleration is equal to the force acting on this electron. So if this is the case, looks like so this electron will now stop, and then will be if there's no boundary, and then this electron eventually the velocity will reach infinity. Of course, physically this is not possible, right? And definitely, so electron will hit the boundary, and you have to confine electron somewhere, right? And of course, when you really reach that kind of a very high speed, and then you cannot use this Newton's second law anymore, right? So that's why this is still limited even in the vacuum case. And however, inside the solid state material, and then there's another mechanism which is very, very important, and that's called damping, right? So why is it damping? This means that you have two types of forces. So one definitely is a driving force, so which is still here, but another force which is proportional to your velocity, but they have an opposite phase. So that basically is the damping force. Okay. So so the damping force typically, since it's proportional to the velocity, and typically what we do with that, we just put this one, and at the left hand side, then you have positive sign. When we move this one to the right hand side, you have a negative sign. So that's why we call it damping force. All right. So, and of course, the velocity itself. Now, what we are concerned, but not the velocity of individual electrons. We should look at the drift velocity. That's because that this velocity, you can see electron will be scattered, right, during this process. So then this, if you look at the average velocity, and because when there's no drift, if you don't apply electric field, and since electrons are moving randomly in all different directions due to thermal energy, right? So if you take average of this, and then definitely will be zero. And however, if you apply electric field, since there's a preferred direction for electron to drift, this is against the electric field direction. And then you take an average divided by the number of electrons, and you find that this drift velocity actually is non-zero due to this electric field, right? And then, so we can use this drift velocity, and then apply this one to Newton's second law, and then you have this the first term, which is the mass multiplied by the drift acceleration, and then so there's a damping force, and then this is driving force. So at a steady state, of course, eventually this Vd will not increase indefinitely; it will reach a equilibrium value. So once it reaches equilibrium value, it will not change with respect to time. So the first order derivative, this will be zero. So when this is zero, and then you have this Vd, which is given by this, right? So this is a very important equation. So now, just for now, we see that so J equals sigma E. So this means that the current density is proportional to the driving electric field, and the proportional coefficient you call conductivity. And then, so in this case, we have the drift velocity. Drift velocity is proportional to electric field as well. And the proportional coefficient in this case, we call mobility. Again, it's a negative sign because the electron has a negative charge. It means that the velocity, drift velocity, is in the opposite direction of the electric field. So if your particle is positively charged, and then you don't have negative sign here, right? So just put this negative sign aside for a while, and just focus on this the relationship, proportional relationship. This means that velocity is proportional to electric field, and then the proportional coefficient mu, which is given by this one, and that's mobility. So basically, it's in here. So this mu is very important. So basically, it tells you that when you apply electric field to a certain conductor, and how fast the carrier can drift, that's determined by the mobility, right? And so this mobility, you can see that it's given by E over tau, and tau is the momentum relaxation time. So basically, it's an average scattering time. So why we call this a momentum relaxation time? And it's because that every time when there's a scattering, so momentum will be relaxed. So why? Because you can see that this electron will change in moving direction. So that's why it's called momentum relaxation time. So obviously, when there's no scattering and this momentum relaxation time is infinitely large, then mu will go to infinity, and then of course Vt will also go to infinity as well. So that basically go back to this case. This means no scattering, right? But this will never happen. Okay. So now it seems that this J is somehow related to the sigma is somehow related to mu, right? Why? Because this just mu just tells you how fast this electron can move, and how much current. So the electron can carry, of course, also depends on and the carrier concentration. So it means that the sigma somehow should be dependent on both the carrier concentration and also this mobility, right? And of course the charge carried by the this as well, right? So this is something we can derive from here. So how to derive this one? So we use it's a very simple model called Joules's model. So in Joules's model, so we basically treat all the electrons separate from each other, and then of course they are doing random movement at the same time. We also doing a drift movement, and then we just try to find a simple average and of the current carried by each electron, and then that you get a total current. Right? That's called Joules's model. So again, come back to this very simple conductor. Say for example, this can be a copper wire, right? And then so it has a length of L, and then have a uniform cross section of S. Now, if we apply electric in this direction, and then the current will flow in this. Sorry, I think current in the electric field should be in the same direction, right? So this means that the electron will move in this direction, the current in this direction. Okay, anyway, so there's a typo here. So I will just try to correct this. And so what happens here that so maybe I just change electric field in this direction, right? So now you can see that electric field and in this direction, and the electron will move in this opposite direction, but the current will flow in this direction. Okay, so this is what we see. So now, so in this case, and so then you can see that if you only look at a very small section of this one, and with a length of Vd tau, so basically it's an average. It's something like a mean-free path, right? So drift mean-free path. So it means that the electron will drift by this distance without scattering, right? So if that's the case, and then you can see that within time tau, and then so within time tau, and then so the number of electrons we should pass through this cross section will be given by the volume of this. So the volume of this basically is this cross section S multiplied by this length, that's this one, and then multiplied by the electron density, right? So that basically be the number of electrons we should pass through this cross section area per time tau. And then we can calculate so what's the current density. So current density is basically current divided by cross section area. And the current basically is the number of charge passing through that cross section area within time tau, and then divided by tau, right? And now we substitute so this one in here, right? And then divided by tau, and there's S here. So now we just put in this delta V. So delta V is this one, and put everything here. And then we can see that the sum of this will be cancelled out. S cancelled with S, tau cancelled with tau, and then G basically E and Vd, right? And then Vd is mu E. So mu is a mobility we just derived, right? So now you can see that if it's NeV, basically a sigma. So it means that sigma is NeV, and then it's related Ne mu and ratio tau by this equation, right? So this is understandable. So now we basically relate the conductivity to mu. So basically conductivity tells you how much current and you can have when you apply a certain amount of electric field to this conductor, right? So of course, how much current you can have depending on so charge carried by the electron and the number of electrons per unit volume, and then how fast you can move, right? Is it reasonable, right? So eventually you have this kind of a relationship. So now we can try to estimate so what's the drift velocity, and then you can realize the drift velocity is actually very, very small. Okay. So for electron density, and so for copper, we know that electron density we have used this electron density several times in this module. And then the Fermi speed or Fermi velocity for copper, we already calculated in previous lecture, and then we just use that value. And then experimental conductivity means conductivity of pure copper, so roughly it's given by this value, right? So if we know this, and then we can calculate so what's this drift velocity because G equals V and E, so that's why V basically G divided by NE. So G is a sigma E. So now, so this is sigma, so is this one. And the E, we can see this is a voltage you across this divided by the length. So we just assume that just this actually is overestimate, okay? So we just assume that the voltage is 1 watt, and then so length is 1 meter. And if it's real copper, if the size is not very small, of course this voltage should be much smaller. This means that VD in principle should be much smaller. But here we just use the logic value. So roughly you can see so what this VD. And then N is this one, and E is the electron charge. So we put all this in and find that the VD is this value. Okay. So this VD, if you compare this with the VF, so VF is the Fermi velocity, so that's given here, right? And then you find that actually, so the difference is about 8 orders. So this means that the electron on the Fermi surface are moving extremely fast. Okay, they have a very fast velocity, but they don't contribute to electron conduction. So the one which contributes to introduction is a very small drift velocity, which is much smaller than the Fermi velocity, right? So that's the picture you usually have. Okay, that's in the basically real space. And then the same electric conduction can be understood much better in the reciprocal space, basically K space, right? So the K space for metal, we already explained this one in lecture 4, right? So what happened that, so for free electrons, and then in the free electron model, so electron will try to fill up the lowest energy first, basically it's 0. And after that, we just move up to higher energy. So eventually, and after you use up all the electrons in the volume, so you end up at the Fermi surface, right? And then the Fermi velocity for copper already is going to use about this order. And then there's no current, net current carried by copper without applying electric field. That's because that for every electron here, you have a K, which is called positive, and then you must have another one negative. And similarly, you have one here and another here. So they're always opposite because this is the center of the K space, right? So that's why eventually they completely cancel out. Means the electric field 0, and then you try to find what's the drift velocity. So every drift velocity is 0. That's why there's no current flowing, right? And however, when you apply electric field, then what happens that this Fermi sphere will drift a little bit, right? So how much will drift? So that basically, and you can calculate from here. So remember, HK is a momentum. So that's why, so delta K, H basically is M multiplied by drift velocity. That basically is a momentum change, right? Average momentum change. So momentum, this is a classical momentum. And then in quantum mechanics, it's H delta K. So this means that when momentum changes by M with D, and then you divide this one by H, and then this will give you the change in this K space, right? And then so VD, we already calculated from previous slides. See what's the VD, and so VD basically is given here. So that's this one, right? So to the electric field, so we substitute this in, and substitute in here, and then this is the one you have, right? So now we put this together, and then you get this value. So that basically is a shift in K space when you apply this electric field, right? So this negative sign just means that charge is electron is negatively charged. So again, you can see that the tau is very large, and of course this is very large because there's no scattering. But because the tau is finite and very small, so that's the reason why you have this. Okay. So now, what's the value of this one? And now we can try to capture this. So for copper, and so we know that VD is equal to this, right? So this one, and then so we just substitute in here because M we know is electron mass, and then we can get the delta K. It's just roughly this value. Okay, it's very small. All right. So this compared to the Fermi wavelengths. The Fermi wavelengths for copper, this we calculated a long time ago, and it's given by this. So this is ratio. So delta K over Kf. So basically, is this delta K over the radius of the Fermi sphere, right? So this is basically is a exaggerated. It means that it's an enlarged view of this, and actually this Fermi surface will not shift by this amount. It will shift by very, very small amount. But it's difficult to see that. That's the reason why we just show that it looks like a Fermi surface shifted by a very large amount, but actually not. So the ratio can see that is a 10 to the power minus 9. This means that it will just shift a very, very small amount. So we can use an analogy. This means that if the Fermi sphere has a radius of Earth, right? So this is the Earth's radius. And then if you use a similar ratio to find out what's the amount of shift of the Earth, so the amount of shift of Earth is 17.8 millimeter. So just imagine if your Earth shifted by 17.8 millimeter, can you notice the shift? Not at all, right? So yet this shift, this small shift is sufficient to give you a very large current, right? So that's the view. So this means that you should understand that so not all the electrons, okay, in reciprocal space, this concept, so not all the electrons contribute to electric conduction. So only those at the Fermi surface, because Fermi surface only shift a little bit. So that basically is this part, right? And because so now this part cannot be cancelled by this part. Okay, so that's why this part is electric conduction, and those inside don't. So that's a picture. But in classical physics, it's different. So classical physics means that so you just do a simple average, right? So if there's a electric field is not equal to 0, and then this will not be equal to 0. So this means that it looks like every electron will contribute to the electric conduction, but some of them will be cancelled out. So that's a classic picture. But eventually, the electrical conductivity which you get exactly the same. But I prefer the picture in classical in the K space because this is more neat, right? It's clean, right? It's basically a Fermi sphere which is shifting, right? Okay, so now if you understand this, now we try to connect these three important physical quantities together, put in the same diagram. Then you see, so the driving force is always the electric field, right? So when you try to drive this and apply electric field to this, so if you go this way, so what do you see? You go this way means that when you drive it, and then this electron will start to drift against the electric field direction, and then you get the current density, right? This way. And so the other way to look at this is to go this path. So when you apply electric field, and then you get the drift velocity. So when you have drift velocity, since this particle is a charge, it's a negative charge, so that's why you get the current, right? So that's why I have so this is the charge carried by electron, and this is drift velocity, and then this is a carrier concentration. So how many electrons per unit volume do you have? And then so this put together and give you the current density, right? So and then from here to here basically tells you how fast the drift is in your kinetic field. So that really is the mobility. So this means that you go this path is more fundamental. It means you have mobility and have a number of the mobility will give drift velocity. And then you have a number of carriers per unit volume. So you combine together and you get the current density. But this one is basically you jump to this step. You just jump to the current density, and then you put all things together. So all this, so mobility and then carrier concentration charge together, then you call conductivity, right? So that's why if in most cases this is good enough because we don't need to care about what carries the current, but we only know that when you apply driving force and then the charge will start to move, and then you get the current density. That's for most of us, this is good enough. But you want to study physics, and then you better go this path, right? This is actually real physics because the mobility is related to this momentum relaxation time, right? But if you go this way, you don't see this momentum relaxation time. But this is a very fundamental. Okay. So I hope you understand this. So now, is a group model good enough for describing electron transport in the conductor? This can be metal or semiconductor. Of course not, because the group model is a very simple model. That's called classical model. So this model is we just do the simple average of the contribution of all the electrons or particles. So we don't care about the quantum mechanics requirement. For example, when one electron occupy a certain K state, because and this velocity is related to momentum. The momentum is the k. And then so once you occupy this one, and then whether the other one can come or not, we don't care. We just assume that all of them can move randomly into whatever direction they can, right? And then we just take a simple average. So this is called Drush model. And then a slightly better improved model we call Boltzmann transport. That's a semi-classical model. So in this model, we do care about the distribution of electron in phase space. So the phase space basically consists of a k space and then the position. So here we only consider the electron in real space. This means the electron moving in real space can be anywhere, right? So we don't care about whether it can go there or not, right? Because we don't care about whether we already have electron there or not. So we have to simple average. But this is different. So this means that in this case, so there's a phase space. It means that if this position is already occupied by one electron, and then of course another electron cannot come if unless this is moved away, right? And then for each electron, there's a probability for electron to occupy this phase space. This means that this probability and there's a distribution. And then if you integrate all the electron in this phase space, if you don't have any electric field, so eventually current density will be zero. So the current density will not be zero is when you apply electric field, and then this distribution will be disturbed a little bit. So this will the change in this distribution function. So once there's a change, and then you multiply this one by this velocity, right? And then just integrate. And then of course the charge here, this actually is an NEV, right? Because it's E and V. So, and then the rest basically is the total number of electrons within the entire k space. And due to this shift in the so-called distribution function, right? So that basically by this. Then you integrate, you get this. So this is more accurate than this one because in this case, you do care about the distribution of electron in k space, right? It means that at each k state, you can only have 2 electrons, right? So it's more accurate. Okay, of course, in this module, we don't look at this, but anyway, this is just in case that if you are doing research in electron transport, you should know what's the difference between the Boltzmann transport and Drush model, right? So now I will use one slide to show you all different regimes of transport, so that although in this module we only use a very simple model, but at least you should know where this model stands in the overall picture, right? So to do this, just look at this simple electric conduction problem again. So say for example, you have a piece of a wire. So this can be a copper, say for example, and then you have 2 electrodes, right? Now, if you apply electric driving force to this the copper, and of course the electron will start to flow, and then so how to describe this electron flow, that depends on to what scale you want to understand this electron transport, right? And so at a very large macroscopic scale, and then probably you have some sort of inhomogeneity inside the material, right? So it means that you have crystal grains, and then inside each grain, and you have a single crystal, but between all the grains, you have a boundary. So this means that when electron moves in this kind of material, definitely electron will be scattered by the grain boundaries, right? So of course, especially when your grain is very small, and then you have a more scattering property issue, right? So of course, if the grain is very, very large, then you don't need to care about it, right? Now, but this is just look at you still treat electron as a particle, right? So the next region, and we look at is we look at inside each grain. So inside each grain, and of course, you still have scattering by defects, and then by lattice vibration, and also by electron themselves. So that's why electron will not go by straight paths. So electron will diffuse from one place to the other place, right? So this means that it will not take a straight path just from this point to this point. And then so before it reach from here to here, and then it will be scattered by many, many times. So this is called classical diffusive transport, right? So this is a region that actually we will use in this module. But the electrons wave, right? So why you don't see electron wave? That's because that it didn't go down to a small enough scale. If you go down to a small enough scale, for example, in this case, if you narrow down and to a very small region, and then you will see electron actually is a wave. So this means that the electron travel from here to here as a wave, come here scattered, right? And after it's a wave, and they can go from here without scatter, also wave, and then they will interfere with each other, right? So that's why when you reach this scale, this is called coherent transport or mesoscopic scale, you actually can see the interference of electrons. So this will give you fluctuations in the conductivity or resistivity or conductance or resistance, right? You see the fluctuation. Why? Because there's a interference between electron waves coming from different directions. Okay. Okay, now, if you go down further, for example, you try to cut this metal into a very, very narrow region, and then in this case, you will see something called a ballistic transport. So what does this mean? This means that when this electron travel from here to here, except for this boundary, and then there's no scattering. So from here to here, no scattering, right? So this means, in principle, if you measure the voltage in electric potential drop from here to here, it should be zero for this transport because no resistance. But in the actual experiment, this is not the case. So what happens in this case that in actual measurement, you have to put your one electrode here and then another electrode here, right? So, so in this case, you basically measure the contact resistance between your electrode and then this is small opening. That's because that your electrode is large enough, and then this electron has to establish equilibrium with the electron inside this electrode, right? But when this electron tries to jump from here to here, and then obviously for electron to travel from this to this through this region, it will feel the resistance here because there's some sort of constraint here, right? It's just like many people try to squeeze to go out from a narrow door, right? So if you feel the resistance, right? Because you want to go out but you cannot go out. Okay, so that because the channel for you to go out is limited, but they have so many people want to go through the same channel, right? So it's some sort of a picture, and then you get, when you measure it, actually get a contact resistance. So the contact resistance for a single channel actually is a most fixed. Again, it's called quantum resistance. So that's why even in ballistic transport, if you measure it, and then so that not mean that you get a zero resistance because you still measure the contact. Now, if we reduce this further and to be much smaller than this mean free path, and then of course we'll see electron as a wave again. And in this case, so this is called quantum confinement, right? So this is the one we talk about in lecture 4. We talk about lecture 3, right? Talk quantum wire. So this is a typical quantum wire. So you have a confinement in the surrounding area, and then so electron is only able to move in one direction. So when this confinement, this region is comparable to the wavelengths of electrons. For example, in copper, so we're talking about the Fermi wavelengths, just a few angstrom, right? So in this case, and then you actually will see this quantization. This means the conductance will become quantized, right? It's not a continuous value. Okay, excuse me. And then you move further. So now you can actually cut this one, completely cut this portion and also this portion, but in between you leave a very small island. Okay, in this case, you'll see something we call Coulomb blockade. So what happened in this case that the small island in between and then form a capacitor, right? So it has a very small capacitance. So once it has a very small capacitance, and then if you want to charge this very small capacitor, and then if you put one charge there, and then you have something like this electrostatic energy given by this one. So this means that when C is very small, and if you already have one charge here, in order to put another charge, since this capacitance too small, and then you need to provide additional energy, right? Just try to imagine that in a wide ocean, you have a very small boat. So that small boat can only carry one person, right? So if you want to jump in, and of course you have to push that person down, and then you can jump in, all right? So if you don't push down, and then you have to apply a very high energy. If you have a large boat, of course, you can just jump in, nobody will care, all right? So that kind of a concept, okay? So that's why, then after that, if you want to jump through that one to another electrodes, the other side. So this means that you have to push this one over first, and then after that, you can jump in. So in principle, so this anyway, this phenomenon called Coulomb blockade. So in principle, you can count the electron one by one, right? So when you have one electron there, you don't have there, and then the energy you need to provide for another electron to go through will be different. So based on this, actually, you can design and fabricate a single electron devices, right? So if you are doing research in this area, you should know, okay? So, but up to now, we still have not talked about the electron spin yet, right? But the electron has a spin, so it means that now we can actually make two small islands here, and then so if an electron has a spin, and then what happens that if you already, if on one island, if you already have an electron with a spin which is pointing up, and then if the next one is also pointing up, it's difficult for this one to come to the same energy level, and then you have to go to the higher one, so that this spin will be parallel to this one, right? So, so this is due to Pauli blockade, this is Pauli exclusion principle. So this means that in principle, you can also control the electron spin by using this kind of, Coulomb blockade. Sorry, Pauli blockade phenomenon, right? And of course, in this case, if you have two islands, actually, you can control the spin in the two islands. So if the two islands are very close to each other, they will actually interact with each other to form a quantum qubit. So which is the fundamental unit for quantum computing, right? So this means that you can see even for this same type of material, you can see that it really depends on to what scale you want to look at the transport, and then you will see totally different things, right? But in this module, we'll only rely on this classical diffuser transport. This means that we're only interested in, how much current this material semiconductor can carry under a certain applied electric field. So that's why we don't look at all this quantum confinement effect, but it's the transport and then Coulomb blockade and so on and so forth, right? So we are somewhere here. Okay, so I hope this provides you a picture on electron transport if you are doing some research, right? I believe some of you are doing research on this one, right? For example, like this conductance fluctuation due to coherent transport, right? This kind of regime. So anyway, this is the scope of this module is just a classical diffuser transport. Okay, so with this, so now we can look at electron transport, electron conduction in semiconductors, right? So electron conduction semiconductor, if you use this diffuser transport model, and so it's very similar to electron transport in metal, but the only difference that now you have two type of carriers, right? So one is an electron and one is a hole, right? So for semiconductor, if we use same concept, so we just focus on, for example, electron first, and so if you don't have any electric field, so electrons are moving very fast, and the holes are also moving very fast inside semiconductor, but the net current zero, right? And however, when you apply an electric field, then both electron and the hole will start to drift in a certain direction, and then this will contribute to the current. So, so this is a current due to electron. So this mu E is electron mobility, and then this is the hole mobility, right? So here, so E is positive. So that's why the current, anyway, I already mentioned before, electron will move against the electric field, and holes will move in the electric field direction. But the current is always in the electric field direction. It's the same. So that's the reason why you can see that if E is positive, so this electron current is in E direction, and the hole current also in E direction. So here, N is electron concentration, P is hole concentration. So E basically is the absolute charge carried by electron, and then this E is the same charge carried by holes. You just ignore the negative sign, right? So that's the expression of the current density. Now, so what determines this mobility? Because mobility is very important, right? And so once you know mobility, and you can calculate the current density. So in semiconductor, this mobility, you can see that basically determined by this momentum relaxation time. So momentum relaxation, and so basically, momentum relaxation time is determined by the scattering events. So how frequent, so this electron is scattered, and also scattered to what direction. That's very important, right? And then, of course, M is important. So M is effective mass. So the smaller effective mass, the larger the mobility. So that's the reason why in the last 20 years, people are trying to, for example, use a string effect to reduce effective mass in silicon, and eventually you have a larger mobility, right? And because tau, you have to reduce the scattering events. So there are three types of the scattering, primarily three types of scattering events in semiconductor. And so we have, so this is actually a well summarized picture, and then this is from and the Professor Dredger Basileska from Arizona State University. Okay, so if you type his name, and then should be found out this one. Okay, this is not from me. Okay, so this is a very good summary. So that's why I just borrowed this, and so you can see that you have three type of scattering mechanisms. One is defect scattering, so basically, and so you have imperfections right inside the semiconductor, and you have this one. And the other one is a carrier scattering. And so this will only become important when you have a very high carrier concentration. And then, of course, the other one is lattice scattering. That's because lattice are always the lattice are always vibrating, right? So you have this lattice vibration wave, and then so in quantum mechanics, it's basically you had a photon, and then this electron and the photon will interact with each other. Basically, electron will be scattered by the photons, right? So for defect scattering, and so the most important one is this point defects. So basically, is ionized donors or ionized acceptors. So this is called point-like scattering potential. So why this is important? Just try to explain this one to you by using this whiteboard again. Okay. Let me go to whiteboard. Okay. When we see electron scattered by a scattering center, so we should have, for example, this kind of picture, right? So this electron come here, and then this will be scattered, okay? And then during this scattering, sorry, this is wrong, this way. And so if this initially is the wave vector k, because momentum has to be conserved, right? So after scattering, you get this one. And then, so this means that, so now the change in momentum. So this is, for example, is k prime, and it's k. So k prime minus k prime minus k will be this one. So because this is k, right? So it'll be this one. So this is delta k. Okay. So this is delta k is k prime, so minus k, because this basically is k, right? So that's from here. Okay. So now, so this is called small angle scattering. So of course, this kind of scattering will affect the conductivity. So that's because that initially this electron is supposed to move in this direction, but somehow it is scattered to this. So that's why actually it goes back a little bit, right? So because it's supposed to move in this direction. So right now it's scattered in this direction, but it's not too bad. But the one which is really will reduce the conductivity is the one we call large angle scattering. So this means that so initially the electron come from here, right? So then there's a defect here. After scattering, so what happens that this electron come here, right? So this will be your k prime, right? And then of course, so this will be your k, right? So then, so your delta k is this one. So now your delta k is given by k prime minus k. So this is called large angle scattering because this angle is huge. So this small angle. So this large angle scattering, the worst case is that it's called uncapped scattering. So what this means that your electron coming here, and after scattering, just go back, right? And then, so of course, in this case, what's your delta k? So your delta k basically is 2 times of this one. So now it becomes like this. So this is your delta k. right? So of course, this completely suppress the electron conduction. Why? Because initially, electron is supposed to move in this direction. After scattering, it just goes back, right? So of course, this will significantly slow down the conductivity. And actually, this makes it impossible to, if all the electrons be scattered back, then it's impossible for you to travel, right? So that's why this large angle scattering is very troublesome, okay? And then, but what can cause this large angle scattering? This means that if this really happens, you need to borrow this amount of multiplied by h, right? You need to borrow this amount of momentum from something, and then phonon cannot contribute this, okay? And then maybe not as large as this one. And then, of course, photon does not provide such kind of large, momentum change. So that's why the only one which you can get actually is from point defects. So what happens that if you have this ionized donor or ionized acceptor, and then if you look at the electrostatic potential, basically have some delta shape, right? So if this is the, for example, ionized donor, so it's negative charge, right? And then that's another donor is a positive charge, right? So and then so positive charge means that, sorry, I said it wrongly. So positive charge, that means that you get this kind of electric potential, very sharp. Right, so this will be your delta V, the electric potential felt by electrons. And then this kind of very sharp electric potential. And so when electrons scatter by this, you need to get a momentum from this, right? So now in Fourier transform, you know that, so this basically is in spatial domain. So if I do a Fourier transform, this one, to the frequency domain, and this very sharp change in the position spatial domain will give you a very sharp change, a very slow change in the K space. So this means that basically you get something like this one, right? So what does this mean? This means that this sharp electric potential in real domain will give you a very broad distribution in K domain. This means that you have many different K vectors which can compensate this momentum change. So if the very large one, say for example, is here, and then just use this one to do this, right? So if you have a very oppositely, if you have a very broad electric potential in a real space, right? And then after Fourier transform, so you get a very narrow spectrum. So this will be K, right? This will be K. So in this case, you can see the momentum, you only have momentum at a very small value. So this means that it cannot help you to have this kind of large angle scattering because you don't have that kind of momentum to borrow from. So you eventually end up with small angle. In this case, of course, your scattering, will not be very important. This is understandable, right? So just like when you drive a car, okay? So if you have a very sharp step here, and then your car come here, of course you feel a large change, right? So, but if you have a very slow, even same height, you have a very gradual change, and then of course your car can move, smoothly, right? It's some sort of thing like this one, right? So your momentum will not change so much, okay? So the same the idea. So this means that this can, of course, in Fourier transform, time domain and frequency domain have same relationship, right? So if you have a very sharp pulse in the time domain and the frequency domain, you have a broad distribution. So you have a very broad peak in the time domain, and you have a sharp distribution in the frequency domain, right? Same idea. So if you understand this, and so now I come back again. So that basically is a something here. So when you have ionized donors or ionized acceptors, so this is a so-called point-like scattering potential, and then this will affect very much your conductivity. And then neutral donor acceptor, of course, will also give scattering, but not as important as this one. Okay. And then crystal defects, of course, now in most materials, you can make the defects density very, very low, right? So that's why in principle, you can ignore this one. And the alloy, of course, if you use alloy, and then you always have this one, right? But this is the average effect, okay? In all the, allow compound, right? And then, so this, as I said, that if a carrier concentration is not very high, just ignore it. Then lattice scattering, and then so you have two types. One called intravalley, and that is intervalley. So intravalley means that within a same valley, and then you have the scattering. Of course, you borrow momentum from the phonon, right? So that's why you have a acoustic phonon and an optical phonon. So the effect will be different, right? Because the optical phonon, you have this non-polar and the polar, and then acoustic is due to deformation, right? And the intervalley, so it means that they actually jump from one valley to the other valley. So when this happens, this typically will happen at a very high speed, okay? And when that field is very high, so when this happens, of course, this will significantly slow down the electron transport. That's because that at the other valleys, and then electron difficult for electron to move, okay? Now, and that's why if you look at the mobility, and so of a typical semiconductor, and so you can see that, so we have this is for germanium, and then this is for hole and for electron. So typically, electron can move faster, right? Because electron has a smaller effective mass, okay? And then the silicon, so you can see that electron, so this is electron mobility, is hole mobility. And so mobility is smaller than that of germanium. And then for gallium arsenide, and then you can see this electron mobility is much higher than that of silicon and germanium, okay? And of course, hole mobility, again, is smaller. So typically, in this kind of materials, you can see that the electron moves much faster. And also look at impurity concentration. This is impurity concentration. So impurity increases, and then typically mobility will decrease, right? That's due to scattering from ionized, impurity levels. Okay. Okay, that's for typical semiconductor. So now we look at this temperature dependence in a more closer way. But again, we use a very simple model to look at this. Okay, and so if you look at this impurity scattering due to Coulomb interaction, so this means that if you have an ionized donor and this ionized acceptor, so ionized donor basically is positively charged. That's why when electron comes, say for example, comes nearby this ionized donor, and then see what happens that so the path will be deflected, right? So this is initially is in the K direction. So after that, it moves to K prime direction. So this means that the momentum has been relaxed. So this basically is you call scattering, right? So electron path has a direction, electron moving direction has changed. And of course, if you have a negative charge, and then so due to repulsive force, and then so this will just push this one away, right? So the temperature dependence is determined by, and so several factors. So the first factor, of course, is the interaction strength, right? So between this one, different temperature, and then next factor is when temperature is different, and then the speed of electron traveling in semiconductor also different. So this means that when you have a same number of impurities, and then if you can travel much faster, and then per unit time, you'll meet more this kind of ionized donors or ionized acceptors. Of course, that will increase the scattering probability. So that's why, so that's, it's given here, say for example. And so the carrier will spend less time near the ionized impurity when they pass with high kinetic energy or speed, right? So this means quantum mechanically, so if this time is less, and then of course the interaction become weaker, right? So that's leads to scattering cross section. So in quantum, so we will not calculate this one. So there's a simple model given in Appendix A, but so it's not so very important. I tell you that this basically, if people have calculated this one, the scattering cross section is proportional to v to the power minus 4. So v is the speed. And then since energy and the v, and so has this kind of relationship, right? So energy is proportional to v squared. That's why eventually you can say cross section is proportional to e to the power minus 2. But E is proportional to temperature. So that's why eventually you can say that this scattering cross section and is proportional to T to the power minus 2, right? And then, so scattering probability increase with number of impurities, right? That's for sure, right? Because you have a large number of impurities, and then you have a higher scattering probability, right? And the next is for the same number of carrier impurity scattering centers, and then the scattering probability will increase with the carrier speed. That's because at per unit time, and if you move faster, and then you'll meet more scattering centers, right? So of course, this is a proportional velocity proportional to T to the 1 over 2, right? Because the T is proportional to energy, and by energy is proportional to V squared. Then you got this one. So that's why eventually you put these three together, and then so when you put these two together, you get temperature dependence, because this one is independent of temperature, right? So the temperature dependence basically begin by the overall temperature dependence of a scattering probability is T minus 2 multiplied by T to the power 1 over 2, you get T to the power minus 3 over 2, right? And then, so if you take this impurity together, and then if you have more impurity, and then so you have more scattering. So that's why eventually the mobility will be proportional to 1 over this, because this is scattering probability, right? And then also inversely proportional to, and this Ni, you have a large ionized impurity, and of course you have a large scattering, and then mobility becomes smaller, right? So that basically is the temperature, and then impurity, ionized impurity concentration dependence of this, this kind of point, sorry, as a point-like electric potential scattering. Okay, so next we look at the phonon, and the phonons are basically initially when electron travel in this direction, and then it be scattered into this direction, and then borrow this phonon momentum, right? So we have two processes. One is absorb phonon, the other is emit phonon. In both cases, and this K prime will change, right? So and then so this momentum has been conserved, and the energy has been conserved. So this is where I will talk about this one in the last slide of lecture 2, right? So that's the vibration, and it can be treated as a phonon, and the phonon is a quasi-particle without a mass. And so remember, we derived this phonon omega Q dispersion, right? And then for phonon inside the crystal lattice, and then we use the quantum mechanics to derive this, and then we get the phonon picture for this lattice vibration. So now we just use that one for scattering of electrons. Okay? So of course, and the density of acoustic phonons in solid will increase with temperature, because phonon is excited by temperature, right? It's proportional to temperature. Okay, so this means the scattering probability will increase with temperature. Okay, and then again, so this is scattering probability increase with the carrier velocity, because that you'll need more phonons, just like in impurity case, right? So that's why the overall temperature dependence is basically this one, and multiplied by this one, and you get the T to the power 3 over 2. Okay, and by the way, and for impurity scattering is the T to the power minus 3 over 2, right? Because we'll talk about the scattering probability. So therefore, this is scattering by acoustic phonon, and so the temperature dependence is for the mobility basically will be 1 over this one, so that's this one. Okay. And then for optical phonon, it's a little bit more complicated. We're not go to details, but anyway, people have calculate this. So even so basically given by T to the power minus 1 over 2, and then multiplied by this exponential factor. Okay, that's due to acoustic phonon. Optical phonon. Okay, so for acoustic phonon, basically given by this one, right? And then carrier concentration, as I said, is only important at higher carrier concentration, which has ignored it. So if you understand this, so now we look at some of the experimental values of the mobility. So in the overall mobility, and so since you have two, if you have two major mechanisms, one is due to phonon, the other due to ionized impurity atoms, right? So that's why since the overall scattering time, and it will follow this Mahinsin's rule. So it means 1 over tau is equal to 1 over tau phonon plus 1 over tau impurity, right? So, and then the overall mobility will also follow the same rule. Okay, so overall mobility is given by this. And then, so different contribution have different temperature dependencies. So this is already explained, right? So the phonon scattering and impurity scattering have different temperature dependence, right? So typically something like this one, if it's an acoustic phonon, and you can see that impurity scattering, and so this mobility is proportional to this. And so scattering is low at low temperature, and then it will increase with, and then the lattice scattering. So you can see that you follow, this rule, right? So mobility will low at high temperature. Okay, so so optical phonons basically follow this rule. That's from a previous slide, right? So if you look at this, so now we look at this mobility, electron mobility in silicon, and then so this is a dopant concentration. So this is a 10 to the power 14, and increase it until you reach 10 to the power 19. Okay, so at the 10 to the power 19, so you can see that this mobility and low temperature is low. That's because that so this mobility basically follow this T to the power 3/2, right? So basically this one. So that's dependence. And then so the high temperature, and it's mainly dominated by this phonon scattering. So that's because you use this rule, right? So when you use this rule, so when this is high, and then you ignore this one, and then so it will be determined by this one. So that's why, so at the low temperature, this mu I, low temperature, mu I is small, and this is large. So that's the reason why eventually is dominated by this one. And at high temperature, so mu L is low and then mu I is large, because mu I will increase with this. So eventually it's dominated by this one. So that's the reason why I have this kind of shape, right? And then when you reduce the dopant concentration, of course, and impurity scattering will become less dominant. So it means that even you go to low temperature, does not mean that this impurity scattering, the mobility to the impurity scattering will be smaller than phonon. So eventually, maybe the phonon scattering, even at a low temperature, the mobility is still smaller than that of impurity scattering. So that's the reason why eventually dominated by this one. And then, so that basically will follow this relationship, right? So follow this line. Okay, so I hope you understand this. And then for electron mobility in gallium arsenide, and then you see the optical phonon effect. So this means that so at a low temperature, and then of course still ionized impurity effect still there. So basically follow this temperature dependence of impurity scattering. But at high temperature, and you see both this optical phonon and then the acoustic phonon effect. Because according to acoustic phonon, and then you follow this line, but actually you can see that it decreases much faster. So this is due to optical phonon effect. Okay, so then you can see it much faster. So it means optical phonon effect is much stronger in the gallium arsenide than that in silicon. So these are basically the mobility of different type of materials. This for gallium arsenide, this is for electron, this is for hole. So you have gallium arsenide, indium arsenide, indium arsenide. So all this low temperature, small bandgap 35 semiconductor. So typically you have a very high electron mobility. But all this kind of material is very typically used because the bandgap is very small. So that's why if you use this at the room temperature, so you have a lot of problems because the temperature fluctuations are huge. So that's the reason why you had to cool down this material to very low temperature, right? And then germanium mobility is higher than silicon, but germanium is not very good to fabricate a MOSFET. So that's the reason why MOSFET has already been mostly realized in the silicon. But in the last 20 years or so, and then people try to look at the silicon germanium alloy, and then so that they can form a heterostructure. So in addition to having a large mobility due to germanium, at the same time you have a string effect. You can basically reduce the effectiveness further, and that will give you a much higher mobility, right? And of course, if you are doing research, you know that now people are looking at carbon nanotubes and graphene. So all these will have a huge mobility, right? But the problem is that graphene is not a bandgap is 0. That's why it's very difficult to use this one as a device, which if you want to use one as in a switch, right? And common nanotube is good, but the problem that it's very difficult to fabricate, and then so you have to make it. Sometimes it's difficult to make it a semiconductor, right? You have a mix of a semiconductor and then metallic nanotubes. So of course, recently people claim that they can actually produce almost nearly 100% semiconducting nanotubes. But even that's the case, you have to be very careful about these numbers when you compare this with the bulk in the material, because the meaning is slightly different. Okay, so for example, for graphene, the two-dimensional mobility, and so it's different from this bulk in the mobility. So it cannot mean that when you have a very high mobility, and then accordingly you have the same enhancement in electric conduction is not necessary. Okay. And then this drift velocity and the mobility. You can see that even you have a finite, very high mobility. That does not mean that when you increase the electric field to a very high value, and then this drift velocity will increase proportionally. That's only true when your electric field is low. So when electric field is low, and then you can see that in principle, there's a drift velocity, following this model, right? The proportional to electric field and the proportional coefficient of mobility, right? So if you want to increase the electric conduction further by increasing electric field, and then you will reach a limit. And actually, for silicon germanium, you can see it will saturate slowly. But for certified this kind of compounds, and you see that actually after they reach a maximum, and they will drop. So this is because that electrons actually will be scattered to a valley, higher valley, and so this means they call inter-valley scattering. And then so when this happens, and actually this mobility will drop instead of saturating, at the high value. Okay, so this is something you have to take into account when you try to design device using C5 semiconductors. Okay, so now let's just stop here for a while, and then later we'll come back and look at this diffusion transport in the semiconductors, because so far we only talk about the drift, right? So we basically assume that the carrier concentrations are uniform. So that's why we only need to be concerned about the drift transport. So we don't need to worry about diffusion. Okay. So after break, and then we look at diffusion transport. Diffusion, sorry, not diffusion transport.